everyone. My name is Emily Heinsen, and today I'll be talking to you about the use of molecular dynamics simulations to predict thymine dimer formation in histone-bound DNA. So a little bit of background. Thymine dimers occur when a thymine found in our DNA has its pi bond excited by UV light. And if it's next to a neighboring thymine, it can create a ring, as seen here, binding those two thymines together. So in our DNA, I don't know how well you can see it, but it creates a lesion within it, which can lead to interference of DNA replication. And these dimers are more frequently found in cells that are exposed to UV light a lot, such as skin cells. And these thymine dimers can lead to apoptosis or even cancer if they're not fixed. And as you can see here, cancer is pretty frequent within the US, especially here in the Pacific Northwest. And it's really important to understand how these dimers interact on the molecular level with one another and within our cells. So luckily there are some repair mechanisms of these dimers. We have the nucleotide excision repair pathway, which physically removes the dimer from our DNA, and then the cut is then repaired by other mechanisms. There's also photolyase, which physically cuts the bond that is binding the two dimers, as you can see in this graphic. Now, unfortunately, those two repair mechanisms can't find all of the dimers, or there is too much damage to fix them. And this can lead to apoptosis or signal cell death, so that it doesn't turn into a cancerous cell. But if there's too much damage, apoptosis might not work, and this will lead to cancer, uncontrolled cell death, or cell division. So this reaction happens on the picosecond time scale and has very low quantum yields, 2 to 3%, meaning that in order for this reaction to occur, those two neighboring thymines have to be properly aligned before that pi bond is excited. So they need to be the correct distance away, which is about 3.5 or 4.2 angstroms. And the dihedral angle between those two also needs to be correct in order for the reaction to occur. So these dimers have been found to bend the DNA. As you can see, this one has no dimers, and the one on the right contains a dimer, and that bending is thought to increase the probability of future dimer formation. We looked at DNA specifically around a histone octamer, because these studies have not been done around such. They're usually on straight double-bonded DNA. And we use molecular dynamics, which uses a set of very complex equations to see where one atom will be in the next moment of time. So it gives sort of a picture of how this molecule will move throughout time, as you can see here. This is just a sample of the movement that the molecule will go through over the course of the simulation. So we looked at if the location of those two thymines around a histone will affect the probability of future dimer formation. And we also looked at if the presence of a thymine dimer already within the system will increase the probability of future dimers forming. So to do this, we created two different systems, so two different DNA strands around histones. One had no dimers, which I refer to as the no dimer system, and another one had two dimers, which I refer to as the dimer system. So we ran 50 nanoseconds worth of data collection, so the little video you saw, about 50 nanoseconds. And we ran this for both systems and used a variety of different programs to analyze them and run these systems. And for analysis, we looked at each of those different neighboring thymine pairs and saw how often they were in the correct orientation in order for that reaction to occur. So there's a lot of data here. The top chart shows the no dimer system, and the important thing here is the average. You can see the dimer system has slightly higher averages than the no dimer system, showing that the neighboring thymines within that system had a slightly higher chance of being in that proper orientation for the reaction to occur. And this is just a chart comparing where those neighboring thymines are located around the histone. As you can see, there are some areas where the two different systems both exhibit higher probabilities and some areas where they exhibit very low probabilities, showing that in both of these systems there are some similarities in regards to areas that will experience high probabilities and areas that will experience low probabilities. So in conclusion, our data does suggest that the presence of a dimer within the system will increase future dimer formation. And there are some minor trends as to where these will form in regards to the histone complex. So for future steps, there is a little more analysis that needs to be done with all the data that we've collected. And I'd also like to create 2 more systems because the dimer system we had 2 different dimers. And I would like to take one of those dimers and put it in a new system and the other one and put it in a different system to see how exactly they will influence future dimer formations. I'd like to thank Dr. Johnson for being such a great mentor through all of this, and my thesis committee, Dr. Yornoff and Dr. Ghazi, for helping me write the thesis, and Suri here at Concordia for giving me this great opportunity.
Avery, thank you. So, your work was done in terms of computer analysis, right? And so, then is this linked to other lab-based data? Explain a little bit about the connection between computational chemistry and other kind of lab-based chemistry for the work that you're involved.
You mean in regards to how the computer analysis?
Yeah, just in terms of the information. So whether that's do you take a starting point from other things that are known from lab-based and then go to the computational stage, or does the computational stage feed information that will be tested in a lab? I'm genuinely asking you because it's not something I'm familiar with.
Yeah, so the 2 systems we got were created from crystallographic systems. So we found those, and then the thymine dimers themselves were taken from a different paper to get the charges and everything. And then we take that system and we minimize it so it's the most stable within the computer system. Is that?
I'll ask the other question. How is the work that you've done here, how is that impacting your thinking about your future, or what kind of plans do you have in the direction that you want to go?
So I'm going to take a year off and then apply to med school, but now I'm thinking about maybe getting into some research because this has really been eye-opening, showing me how pretty cool research can be. So I'm not really sure where it'll be.
Okay, that's fine.
So in the slide where you had both the dimer and the no dimer systems, and they're kind of following each other. Yeah, so does that give you any information about maybe some structural motifs within this DNA wrapped around the histone core? Because they're similar, right, except the dimers, the presence of the dimers.
Yes.
So would that give you any information about the structural motifs as that's wrapped around causing differences?
Yeah, so it shows that within both the systems, there are these areas that are hot spots within both systems and areas that are low spots. So it shows there are some similarities between the systems. But then there are areas that are vastly different. So those could be caused by the dimers, since both sequences of the systems are the same.
Where there's differences, is that close to dimers usually?
This one is, and these ones are. So somewhat.